Hello students, today we will be learning about how to draw the velocity diagram of various mechanisms using the relative velocity method that comes under the graphical method of velocity analysis. For this, using an example of swing machine head mechanism, which is actually responsible to actuate the needle bar. So the example which we have taken is as follows. The problem statement is like the mechanism shown in the figure is used in the head of a swing machine to actuate the needle bar. The link 2 is the driving crank, which is assumed to rotate clockwise at a uniform rate of 10 radians per second. Link 6 represents the needle bar, which reciprocates vertically. Draw the velocity and acceleration polygons and find the velocity and acceleration of the needle bar and the angular velocity and angular accelerations of link 3, 4 and 5. So this is the configuration diagram of the mechanism. We can see that points O2, O4 and O6, these are the fixed points of the frame of the swing machine. Link O2A is a crank which is rotating in the clockwise direction, and this link OA is connected to the ternary link at the point B with the help of a link AB, and further the ternary link is connected to the slider, that is a needle bar D, with the link CD. The slider will be moving in the vertical direction, and so the needle will be moving up and down. This is the configuration diagram. We will be, in today's lecture, we will be only looking at the velocity diagram. In the second part of this, we will be looking at the acceleration diagram. So to draw the velocity diagram, we are given the angular velocity of the link OA. With the help of that, we will calculate the linear velocity of the link OA by the formula V is equal to R omega as follows. So the velocity of point A relative to O will be given as O2A into omega 2, that is 0.025 into 10, that will give you 0.25 meter per second. There is a small correction here. Now to draw the velocity of the link OA, first we take a point, and on this point we have O2, O4 and O6, because all these 3 points are fixed. Now, as we know, the velocity of any link is perpendicular to the direction of the link. So, we will draw the velocity of link OA in the direction perpendicular to the link OA from the point O2 as shown here. The length of this velocity vector O2A will be equal to 0.25 meter per second, taken in a linear dimension through a scale. We will be converting this 0.25 meter per second into a linear dimension by taking a proper scale. This is how we get the point A. So vector O2A is representing the velocity of link OA. Now to get the velocity of link AB or the point B, we draw the velocity of link AB by drawing a perpendicular to the link AB from point A in the velocity diagram as shown here. As we don't know the magnitude of this velocity, So we just draw a line which is perpendicular to the link AB. Now to get the point B, we can draw the velocity vector of link O4B from the point O4 in the velocity diagram. The velocity vector of O4B will be perpendicular to the link O4B as shown here. So, by the intersection of the velocity vector of O4B and AB, we get the point B in the velocity diagram. And also we get the velocities of the link AB and O4B. Sense of the velocity of point B will be according to the relative velocity, as the velocity of B will be equal to velocity of A plus velocity of B relative to A. So we draw the velocity vector of link BC that will be perpendicular to the link BC, and we draw the vector from the point B in the velocity diagram. So the intersection of the velocity vectors of the link O4C and BC will give us the point C in the velocity diagram. Now, to get the velocity of point D, or to locate the point D in the velocity diagram, we have the link CD. So we draw the velocity vector of the link CD that will be perpendicular to the link CD, and we draw the vector from the point C in the velocity diagrams as shown here. Again, as we don't know the direction and magnitude of the velocity of link CD, so we just draw the velocity vector from the point C. Now we have the slider D, which is always moving within this guides. So the direction of movement of the slider will always be in the perpendicular direction. So the velocity of the slider will always be in the perpendicular direction or in the vertical direction. So we now draw the velocity of the link O6D, that is the slider, from the point O6 in the velocity diagram in the vertical direction as shown here. The slider will always be moving in the vertical direction. So the intersection of the slider velocity and the velocity vector of the link CD will give us the point D in the velocity diagram. Again, the sense of the velocity of the point D will be according to the relative velocity, that is the velocity of point D will be equal to the velocity of C plus the velocity of DC. So this is the velocity diagram of this mechanism, and we get the velocity by measuring the velocity vectors. We get the velocities of each and every link of the mechanism. As follows. So velocity of link AB will be 0.2675 meter per second. Similarly, the velocity of C relative to B is 0.18 meter per second. Velocity of D relative to C is 0.105 meter per second. Velocity of point B, which the frame, is 0.2825. Similarly, velocity of point C with respect to the frame is 0.335 meter per second. And from these you can also calculate the angular velocities of the links as follows by using the formula V is equal to R omega. So we get the velocity of link BA as 2.675 radians per second in the counterclockwise direction, and velocity of B as 7.063 radians per second in the counterclockwise direction, and the velocity of link DC as 1.05 radian per second in the clockwise direction. So this is the velocity diagram. In the next lecture we will see how to draw the acceleration diagram.